Thanks for the invitation. I'm really, really sorry I can't be there in person. I was planning on coming, but nothing to do with COVID. I just didn't for various other reasons, I couldn't make it. And probably many of you were in the same position that I am, in that the very last conference that got canceled just before COVID was Dipendra's conference in India, which we sort of, got almost to and then got canceled at the last minute. And I was really looking forward to this being my first foray out into the world of mathematics, but I'm going to have to settle for Zoom. I really dislike Zoom personally, and the one thing I find very difficult about it is the lack of feedback from the audience. So I'd like to encourage everybody to do two things. One is to feel free to interrupt me and ask questions, and the other is to turn on your cameras so I can at least see you nodding or sleeping or whatever it is that you're doing. So I just want to say a few words about Gordon. I've known Gordon for a very long time, since around 1981 or two. I think I've known him longer than anyone else here, except with the exception of Marko Tadic, who I think has known him since before that. It's really remarkable to me that we've become the senior members of the field. It's a little bit scary. I'm now typically the oldest or one of the oldest people at conferences that I attend, and I don't know how this happened. I've known Gordon for a very long time, and I've had frequent contact with him over the years. The first extended conversation, I remember well, the first extended conversation we had, it was, I don't know what year it was, but it was in the early 80s, I think, at Utah at a conference. And I had lectured about my thesis, which had to do with real dual pairs. And Gordon asked me many, many questions about it and really wanted to know everything. And he basically kept asking questions until we got to the point where I couldn't answer his questions anymore. And he's been writing papers on the subject ever since. And very beautiful, some of them very beautiful papers, I should say. And I don't mean to take credit for Gordon's interest in the subject at all. He was just sort of grilling me about my thesis. I had spent a lot of time with Gordon's thesis, which had a big effect on me. And to this day, I still think there's some interesting geometry behind his thesis that no one's figured out, unless actually somebody has done so in the intermediate in the past 40 years that I didn't hear about. And then I'd like to skip ahead to about 5 years ago. Gordon sent me an email with some very particular questions about representation theory of spin 4-4, the real simply connected group of type D4. And he and Witek, I believe it was, were working on a paper, and they had some very interesting, unusual calculation that they wanted to do using Atlas. So I'm one of the members of the Atlas of Lie groups and representations project, which is a computational project in Lie theory. And there are lots of calculations that we can do. And he wanted to know something. It was a very unusual sort of question, when I would have thought of about something about the looking for representations of this group, all of the representations with a given infinitesimal character having a certain property. And basically everything he wanted to know was true. We confirmed it, and all of his intuition and guesses and calculations were correct, with one exception. There was one particular K-type calculation where our answers didn't agree. And I kept insisting that the software is telling me that this K-type does occur or doesn't, I forget which it was. And Gordon wouldn't take that for an answer and insisted that he knew that the opposite answer was true. And I'm always very impressed by these people that can do this sort of thing, where they do a calculation in their own way, often a very difficult one, and they're so convinced of the answer, they stick by it. And in this case, it took a while, but Gordon, of course, was correct. And there was a bug in the Atlas software that we've uncovered this way. And I think this was one of the deepest bugs that we found. It was buried deep in some algorithm that rarely had an effect on anything that we'd ever noticed. And that was an example of Gordon's skill. I've always had a lot of respect for Gordon, the time and energy he spent with students, and his worldwide network of collaborators, and his approach to mathematics. So I'd like to segue into my talk now. I'm sorry that I'm not talking about minimal representations or theta. Actually, the last paper that I wrote on the subject was with Gordon and Dipendra about 5 years ago. It's actually one of my favorite papers, if only because of the informal title, which is the Theta Correspondence for Dummies. I wanted to have that be the actual title, but I got overruled. But that was a wonderful collaboration. We brought together 3 people with rather different backgrounds, and something very nice came out of it. So with that, I'd like to begin. And so let me reiterate, excuse me, let me reiterate that I'd really like to encourage people to interrupt me. All right, so subject is Arthur packets. And I think many people are familiar with the basic setup here. We have a map psi. Well, I'm just going to talk about the real case, the Weil group cross SL2C into the L group of a reductive group. And well, maybe right here I'll say, for starters, the Weil-Deligne group of a local field. And Arthur conjectured that associated to such a map, oh, and sorry, I forgot to say, this satisfies some properties. In particular, psi restricted to the Weil-Deligne group is a tempered L parameter. And on SL2C, it's algebraic. Arthur conjectured that associated to such a thing is a finite set of representations satisfying various conditions. And this has become known as, these are known colloquially as Arthur packets. So I should say this is a conjecture, and it's an extremely general conjecture for really in this generality, and not that much is known about them in that generality. So I'll just say a note. There's no general definition of an Arthur packet. In this setting, that is to say, Arthur conjectured the existence of these packets with certain properties, but didn't explain how to find them in the end. And the properties, the required properties, do not uniquely determine the packet. So I'm drawing a distinction here, which is it's possible to make a definition which uniquely defines something, but you have no idea how to compute it. But in this case, neither is true. We don't even have something which uniquely defines it in general. And I'd also like to say that there are more general Arthur packets than these. This theory is especially over R. There's quite a lot of work about this. And for example, just to get the oscillator representation into the picture once. The oscillator representation of SP2NC is not in Arthur's list. It is not a pi in one of these pi of size. And clearly, excuse me, clearly the oscillator representation, whatever definition you have for Arthur packets, especially unipotent packets, which I'm going to talk about in a minute, the oscillator representation should be one. So there's definitely a lot to do to understand what the generalizations of Arthur packets are. And in particular, there's a lot of interest in in the oscillator representation of the metaplectic group. And the reason I say things in this order is that, of course, Arthur's original construction only applies to algebraic groups. So certainly there should be some extension to nonlinear groups like the metaplectic group. And there's quite a lot of interest in that. But even if you stick to linear groups, for example, SP2NC, this is an algebraic group. And so there's sort of two different levels of generalization here going on. We pause there. Questions? Okay. Well, there are two constructions of packets. Arthur, in his book, gave a construction of pi of psi when G is GLN SP2N or ON quasi-split. In other words, classical, well, sometimes people say classical groups. I think there's a little note of asterisk there. These are, first of all, quasi-split classical groups. And second of all, when one says classical group, maybe you include things like spin groups and adjoint groups and so on, and those aren't covered. These are the groups which are covered by Arthur's construction for any F. And in ABV, I'll use this notation frequently to refer to the book by myself, Dan Barbasch, and David Vogan, 92. We gave a construction of pi of psi for any real group. And I should reiterate here that I'm always talking about G of C is a connected complex algebraic group, and G of R is its real points. That's always the setting of this stuff. And so it's long been expected that in the case where both of these constructions apply, well, I should say, Arthur constructs these packets explicitly. He gives some properties of them. And in ABV, we give I should use the right notation. I call these AR and ABV. We give this construction, and it's long been expected and assumed, and it sort of has to be true that these two constructions are the same. Is it true that pi ABV of psi is equal to pi Arthur of psi? In the case of GL NR SP2NR and O NR quasi-split. And this is long believed to be true. Theorem. This is due to the result of Arancibia, Mezo, Mezo, Nicolas Arancibia, Paul Mezo, and myself. I'll explain why I wrote this in this way in a moment. In this case, if G is one of these groups, GLN, R, SP, and O, quasi-split, as I said above, then first of all, if G is not equal to O2N, R, quasi-split, and we're given an Arthur parameter psi, then pi of psi and pi ABV of psi are equal. If G is equal to SO, always when I write O, I of course mean SO. If G
Jeff,
is
what is the QS subscript?
Quasi-split.
But you've written the group though, no?
So maybe what you mean to say is SON quasi-split means SO N N SO N plus 1 N, or SO N plus 1 N minus 1 2N plus 1.
So you mean any quasi-split form?
So SON doesn't mean a compact group. It means an n-dimensional orthogonal group quasi-split form.
I see. Thanks.
If G is SO2N R, is equal to this, quasi-split, then what's true is that the Arthur packet is equal to the ABV packet, union the ABV packet for psi upper epsilon, where epsilon is the outer automorphism of SO coming from O. So Arthur's result is a little bit weaker. There's a finer decomposition on the ABV side, so you just have to take this outer automorphism into account. That's the theorem. These two things are indeed equal.
Hey, Jeff.
Yes.
How about unitary groups?
Mezo and Arancibia are in the process of doing unitary groups.
Oh, okay.
Jeff, in Arthur's book, he works with orthogonal groups, as you said. So when you say the Arthur packet is the union of this, so what do you mean?
I think that sort of explains what I mean here. So for an even orthogonal group, so I think pi Arthur of psi, it's a set of representations pi of the orthogonal group. And so that's what this means. For odd orthogonal groups, for odd orthogonal groups, it's a minor point. But for even orthogonal groups, Arthur's packet, as you say, is representations of O2N. So that's sort of the only possible result you could have.
Okay, so it's not, it's the natural result is not unexpected.
That's correct, right. Yeah, yeah, and so just to say it again, I guess in this statement, well, yeah, there are two ways of understanding the statement. The way I intended it is that I'm thinking of the author's definition as he gives you a set of representations of O to N, restrict them to SO to N, and then you have this equality. Okay, other questions? Okay.
That's good.
What about the complex numbers?
Sorry, complex groups. That's complex groups. That's an excellent question. I'm not sure what Arthur says about that. I know that for the ABV construction for complex groups goes back to so for over C, ABV is really just BV from the 1980s, I forget. And I'm not sure what Arthur does about that, but whatever he does, they have to be equal. Okay, that's the end of my talk. That's what everybody wanted to know. I'm kidding, actually. I'll say a little bit more, but probably most people in the audience, that's what you wanted to hear. The answer is yes. But I want to give just a little bit of an overview of the proof. I should say of the ingredients of the proof. And it's a rather high level overview because it's pretty technical. And it's hard to say, it's almost impossible to say everything. So let me just give a quick survey of what this result says. So I'm basically going to just talk about the ingredients of the proof. So the first thing is Arthur's construction. So I'm going to illustrate this just to avoid having to say a lot of words. I'm just going to talk about the case when G is sp2nr and when G is sp2nr. And you take GL to be GL 2n plus 1 R. And the dual group of GL is GL 2n plus 1 C across the Galois group. And this comes with the natural automorphism delta is transpose inverse. And I'm just going to use the same terminology for transpose inverse on this side. And this group, GL upper delta naught is SO 2n plus 1 C. So I'm going to write down here the group, what did I call it? LG. Let LG be SO 2n plus 1 C. This L group. This L group naturally embeds in here. So again, the starting point is this group is the fixed points of an involution of this group, and then there's something to do with the extension. And the dual group, this is on the dual side. LG is the L group of SP 2n R. That's why I chose these numbers. And then what Arthur said is that if you're given a map from the V group into LG,
Jeff?
Yeah.
Is it really the same delta on both sides?
No.
Okay.
Well, what do you mean by same?
I mean, it should be some dual delta on the dual side.
No, but good. That's an excellent question. It's not the dual delta. The dual delta, I think from the way you're thinking of it, would be the identity, but it's not. They're
Right.
both transpose inverse. This is not sort of a Vogan duality sort of thing. It's really transpose inverse on both sides.
But isn't the L group of an algebraic group constructed using some dual delta?
I don't mean to say that delta is in here. I'm saying that this group has this extra automorphism on it, which is delta. The L group is just the cross product, and then there's there's this twist, which given by transpose inverse.
I see.
Right, and you have this picture. And by the, I'll call this epsilon, and by the general principles, there's some relationship between the representations of G and GL here, and the situation is the following. So here's how Arthur defines pi psi. He says you start with psi, and then you compose it to make a map into GL. And it's known how to make an Arthur packet for GL. That's well understood. And this is a singleton. Right, and now, excuse me, there's some twisted theory here, which is this is a representation of this group GL 2n plus 1r. You make the group GL 2n plus 1r semi-direct delta. And this pi that you've got here is fixed by delta. That's for free from the construction because it factored through this fixed points of delta. And so you can extend it to a representation of this extended group. This is standard Clifford theory. If a representation is fixed, it extends in two ways to a representation of this extended group. And Arthur chooses one of them using Whittaker. Using Whittaker models, you can choose one of these extensions. And what do I want to say next? So that's oh, right, and then pi tilde GL, right, and this thing has a twisted trace. And the twisted trace is basically the trace of pi tilde GL near the point 1 cross delta, not near the identity, but well, I shouldn't say near 1 cross delta, on the coset GL 2n plus delta. And there's a theory of twisted endoscopic lifting. I'm going to write that as delta lift. I'll put Arthur's name here, of eta is equal to the trace, twisted trace of pi tilde G sub L. Definition. So there's a notion of twisted endoscopic lifting which takes stable characters of this twisted endoscopic group. I didn't use those words up here, but I could have. This is a twisted endoscopic group. So the picture here is, the idea here is that ordinary endoscopy says that if you have an L group and you take a semi-simple element of that L group, take its centralizer, identity component, and then you take the dual group, that's an endoscopic group, and there's a theory of endoscopic lifting. And the twisted endoscopy is the same picture where the automorphism here isn't required to be inner. It just has to have finite order. In this case, it's this automorphism of order 2. And there's a whole long theory of this due to Kottwitz and Shellstad and so on. That's what we're using. And that defines this twisted lift, taking stable characters on SP to twisted characters on GL. And you define eta to be the stable character of SP2NR, whose lift is this given twisted character. And excuse me. And then pi of psi, it's the set of pi, a pi occurring in psi. Occurring in eta. Eta is a finite sum. It's a sum of characters. Maybe I should write theta pi I. It's a sum of characters, and by definition, the packet is the representations which occur in that character. Okay, so all you need to do in order to understand the details of what I just said is read Arthur's book. I believe you can understand the outline of what I just said by reading the introduction, but there's a tremendous amount of work that goes into that, of course. All right, let me pause there. Questions? All right, so that's Arthur's definition. What about ABV? Well, ABV is completely different. And here's an overview of the ABV construction. So for simplicity, I'm going to fix lambda a regular integral infinitesimal character for SP. And there's a variety x lambda it's described in ABV. I'm not going to give its definition here. I'm just going to tell you its properties. It's a variety with an action of this dual complex group check G, which I'll remind you is this group SO2n plus 1 C. With an action of this complex group on it. It's a complex algebraic variety. It's complex algebraic variety with finitely many orbits. And it has the following properties. One, the orbits on this variety are in bijection with the set of homomorphisms of the Weil group into LG with infinitesimal character lambda. Period. Well, up to conjugacy.
Divided by G check.
Yeah, up to conjugacy. So there's a notion of admissible homomorphism, standard terminology for maps of the Weil group into the dual group. And in the real case, there's an elementary invariant attached to such a map, which is its infinitesimal character. And it's natural to look at the representations with a given infinitesimal character. By Harishchandra, there's a finite number of representations, irreducible representations with that infinitesimal character. And so that cuts us down to a finite space. And this space, the orbits on this space is exactly capturing these homomorphisms. And the second statement is that there's a description of this space as the disjoint union of certain spaces that look like this. So check G, remember, is this SO 2n plus 1C, and check B is a Borel. And so check this this check G mod check B is the flag variety for the dual group. And these check, this is a finite union. Each check Ki is the fixed points of an involution of check G. That is to say, each check Ki is the complexified maximal compact subgroup of check G. So this space on the right for a fixed check K, it's the K orbits on G mod B on the dual side. And that's a finite set. And this is very well understood. The closure relations of these orbits have to do with the Bruja order. And this is a familiar setting for doing geometric representations and D modules and things like that. All right, let me pause there. Questions?
The I.
Sorry, what?
Can you repeat?
So the last sentence, is it G check or G check theta I? Or,
Check Ki is the fixed points of theta I acting on check G. And this is the complexified maximal compact subgroup of check G.
Of a real form of check G.
Complexified maximal compact subgroup of a real form of check G. That's correct. Other questions? Okay, so let me just say one other word. If the space X lambda, excuse me, it's a quotient of the set of maps from WR into LG. And the key word to search on here is canonical flats. In ABV. In the p-adic case, the corresponding thing is just X really is just the set of maps from the Weil-Deligne group into the dual group. There's no funny quotient required. That's the difference between the real and the complex real and p-adic cases. And for a discussion of this, see Vogan local Langland's conjecture from 1990. I don't know, no, later than that. Local Langland's conjecture, the 90s. All right, so where am I? Well, so this space here is parametrizing maps of the Weil group into the dual group. And well, we're interested in the in a refinement of this. So remember, given a map of the Weil group into the dual group, associated to this is an L packet. And we want a refinement which will actually pick out individual, look at the structure of this packet. And for that, we introduce the following. I'm going to say Xi is a pair check O tau, where check O is a check G orbit on X lambda. That is to say, it corresponds to a map of the Weil group. And tau is an irreducible local system on that orbit, which is to say it's an irreducible representation of the centralizer of a point in the orbit, the component group. Okay. And very roughly speaking, back in the old days of Shellstad and Langlands and so on, it was well known that the representations in an L packet are somehow related to characters of the component group of the centralizer. And this is a precise statement of that. And the statement is the following. Well, given Xi, you can construct the following objects. You can construct an irreducible representation pi of Xi, which is an irreducible representation of this group G of R. So that is to say, excuse me, this is a precise version of the thing I just mumbled about. Check O gives you an L packet, and the additional information of check tau actually picks out a representation in that L packet. This is contained in pi of phi. It also hands you a so-called standard module. This is a induced from discrete series or limit of discrete series, and it's reducible, but its unique irreducible quotient is this pi of Xi, unique irreducible quotient. So this is a precise and extended version of the Langlands classification. Every irreducible representation is realized as the unique irreducible quotient of a certain standard module. And that's all going on the group side. And on the dual side, associated to Xi is a natural constructible sheaf. Constructible sheaf on X lambda, which is where you take the local system and extend it by 0. Extend by 0. And there's a natural perverse sheaf, which is the middle middle intersection, the middle extension, the perverse extension. Reverse extension. And you have the following picture. So we have pi of Xi and I of Xi. And these both, these give you the K group. How did I write it? K pi. And I'm suppressing the lambda, K pi lambda. This is the set of virtual characters of G with infinitesimal character lambda. So this is a Z module. When I write K, I'm talking about the Grothendieck group, so you're ignoring extensions. Everything's completely reducible. And this space is literally, you can think of it as the formal linear combinations where pi I is irreducible with the given infinitesimal character, and some finite sums of virtual characters. And it's a basic fact that the pi's and the i's span the same space. Such that ij is standard. This K group, the virtual characters, has two different bases, the irreducibles and the standards. And the change of basis between the two of them is the Kaiser-Johannistic polynomials. There's a dual picture on the dual side, mu of xi and pi of xi. You can identify their K groups. I'm going to just call it K X. They have the same K group, and very similar. You can think of an element of this group as either a linear combination of these mu's or a linear combination of these perverse sheaves. Excuse me. And the theorem, I like to call this Vogan duality. This version is in ABV, but it goes back to earlier work of Vogan. There exists a perfect pairing, K pi cross K X to Z, perfect. Well, that's sort of obvious because I've just told you that this side, both sides are parameterized by the same data, these local orbits and local systems. And so they're two Z modules of the same rank. You can obviously define a pairing. You could define it like this. You could define, which way did I do it?
Jeff?
Yeah.
I'm a little confused. To get an actual bijection, don't you need to consider on the group side various real forms?
Yes, I'm gonna say a word about that in a minute. So you define this to be plus or minus delta xi prime. And in this talk, well, I'm almost done, so it's hardly going to matter, but plus or minus always means an elementary sign. There, a lot of the hard work in this project is getting some difficult signs to work out, but this isn't one of them. So that's a perfectly good definition, where you use the standard modules as a basis on one side and constructible sheaves on the other. The other thing you could do is you could define it like this: pi of xi p of xi prime is equal to plus or minus delta xi prime. And the theorem is that these both hold. That is to say, if you define the pairing this way, it satisfies this property. And so that's a very deep and intimate connection between the representation theory. Where's my picture? Well, so that's a close relationship between this K pi and Kx, the representation theory on one side and the geometry on the other. And so now let me mention this asterisk that Lucas asked about. A lot of what I'm saying is not entirely precise. To be precise, you need to talk about strong real forms, and also the notion of pure real forms on the group side. There's lots of places where you can read about this. And for GLN, actually, in this case, it doesn't matter. In the case of, it's totally okay, everything I'm saying, when GL is, when G is GL 2n plus 1R. Because in that case, there is only one real form and there's only one pure real form, and everything I said is literally true. In general, you need some extra words. Questions? All right, well, let me just, I guess I'm going to finish by telling you what ABV packets are. I should have known I wouldn't get any further than this. Corollary, K pi is isomorphic to Ham sub Z of Kx into Z. All right, that's what a perfect pairing says. And so in order, K pi, these are the things we're interested in, virtual characters. We're going to obtain them by finding elements in the dual of Kx. And just very briefly, here's the definition. If P is a perverse sheaf on X, and O is an orbit, you can define chi O of P to be a certain multiplicity, the multiplicity of the cotangent bundle of the orbit in the characteristic cycle of P. All right, that's a lot of words, but this is contained in this Ham Z Kx space. And definition, pi, well, so let me write it this way. Psi, we're given an Arthur parameter. We're going to map it to phi sub c, which is a Langlands parameter, which is, oops, this is a standard construction in Arthur. Given an Arthur parameter, there's just always an associated Langlands parameter. And that gives us our, this orbit O on X. And we get this character chi sub O. And by this duality, we get a virtual character in K pi. And that defines K pi. And then pi ABV of psi, it's the set of pi occurring in this virtual character. And then the theorem is that, well, I told you the two packets agree, and well, in fact, these etas agree. Eta psi Arthur is equal to eta ABV, eta psi ABV. All right. So, well, I hope I've convinced you that proving that these two things are equal is a non-trivial project, because the constructions are entirely different. And I'll just say a couple of words about, how do you prove this? Well, there's the key point is that in ABV, if you look at chapter 26, there's a theory of endoscopic lifting, which I'll call lift ABV, taking stable characters on G to a twisted endoscopic lifting, I should say, twisted on GL. And this is entirely in terms of this this duality. And so there are two things that you need to do. One is to prove that this lifting as defined by ABV is the same as this lifting defined by Arthur. So these two functors are, well, I'm sure they're functors. These two constructions are the same. And you have no hope of proving this thing from first principles. You just compute both sides. Compute both sides on standard representations. And it's not easy, and there's a lot of details to check. In particular, there's extensions and so on. But anyway, you prove this, and then that tells you that you have to prove that the lift ABV of how did I write it? ABV of eta ABV is equal to lift yeah, right, is equal to lift Arthur of eta Arthur. So Arthur defines this by this property. And if you can prove this equality, that's what you need to prove these two things are equal. And let me just say, well, there's a lot of calculations and there's a lot of details to check, but in outline, it follows the chapter 27 of ABV, which is about endoscopy, but you need the twisted versions. And there's a lot of details to check. And let me just conclude by saying, I meant to say this at the beginning, by way back here, I said something which I forgot to go back to. The theorem I stated, I'm using scientific notation for the authors. I consider myself the third author here, even though alphabetically I'm first, in that this theorem is really due to Arancibia and Mezo. They had the whole outline of the proof for a long time. They had some technical help at the end, and that's where I came in. And with that, I'll say thank you.